All right, let's start the lecture 2, microfabrication, and then we start with the lithography. Okay, so to fabricate it, to fabricate MEMS device, and everything start with the lithography, photolithography. Well, some of you already know this, but I want to kind of describe briefly each step of the lithography. So the photolithography, actually the this is the optical pattern transfer technique in which the micropattern is transferred from a photomask to an UV sensitive polymer layer coated on the substrate. So the UV sensitive polymer layer we usually call the photoresist. Okay, and then as is shown um, in this figure over here. So bottom layer is the substrate. It could be silicon wafer or glass wafer, and then before put them into the photolithography machine, actually we put the photoresist on top of it. Okay, so that's photosensitive polymer, and then on top of it, actually we put the photo mask shown on over here. So in the photo mask, in this figure, there is a pattern. Over here, there is a rectangular pattern in front of the mask. Okay, and then the pattern was located on the surface of the photo mask that is actually facing to the photoresist. Okay, so and then the gap between the two, like a photo mask to the photoresist, sometimes it could be contact, like sometimes they maintained with uh, very small distance, right? So like probably few micron, okay. To avoid any like damage onto the photo mask, photoresist and the photo mask as well. Okay, so in that situation, okay, and then if necessary, there is some alignment steps should be done to align the pattern on the photo mask to the pre-existing substrate on the wafer. Okay, and then everything is ready, and then sometimes under the vacuum condition, okay, and then to maintain the distance between the two in like in secure, and then the UV light was exposed from the top to bottom, right? So it's shown in this figure. The UV source was located on top of the photo mask, and then through the certain optics, and then all the UV light like controlled in parallel way, and then it was exposed. Okay, and then well, depending on the photoresist that deposited on the top of the substrate, there are two kinds of photoresist is available. One is called negative photoresist, and the other one is a positive photoresist. Okay, so the difference between the negative and positive photoresist, it depends on, well, basically. Let's talk about the photoresist, positive photoresist first, and then there is, well, in over here, because the pattern on the bottom photo mask over here is this is like a uh, blocked, the blocked scale here. So when the UV light exposed, like blocked one is maintained its own photoresist properties, and but the other side, right? The other side was exposed by the UV light because it's not protected by the photoresist, right? Only this scale region was protected, right? So this like a C shape of the photoresist was exposed under the UV light. And then if we put this, if the vapor with this exposed photoresist was exposed into the developer, okay, then the exposed area by the UV light was developed, and then eventually it was removed, right? So positive photoresist, right? UV light actually uh, react with the positive photoresist. The uh, so expose the area positive photoresist that on the exposed area. So photoresist and that photoresist react with the UV light, and then it was removed by the developer. Okay, but the other hand, in the negative photoresist on exposed area was react with the with the uh, with the developer. Okay, so unexposed area is removed in negative photoresist, but the other end exposed area was reacted with developer. Okay, so so that's the difference. Okay, so I mean sometimes you may have questions whether either positive photoresist is better than the negative photoresist. So it depends on your application actually. Um, so we're going to talk about it eventually, but usually positive photoresist is used for the um, uh, some etching process, not the etching process, it's a more to thin metal pattern on the uh, using the E-beam evaporator. Usually positive photoresist was used because it's a relatively easy to remove. We're going to talk about this more detail. But if you want to use this exposed uh, negative photoresist as like a structure later, right? Then, for example, or to should be withstand the long step of the etching process, then negative photoresist is preferred because it's more robust, and then it withstand more reactant later. So its mechanical properties is better. Okay, so that's why you have kind of some choices to whether you go for the positive photoresist or negative photoresist. Okay, so after, for example, after this expose, and then if you deposit, for example, on metal, right? Then what happens is to make this pattern, for example, or in this case, you put like a metal on top of it, and then if you let's see, no, oh, this is for the negative direction. I'm sorry. All right, let's go to the negative photoresist, and then if you want to deposit the material, and for example, this is yellow is like for example, this is a metal, and then if you deposit the metal layer on top of it, then exposed area, the metals will be remained after remove this photoresist, and then the exposed area is gone. But if you want to etch the exposed area, then if you put this wafer with the patterned photoresist on the etchant, then only exposed area is removed, and then protected area will stay. So at the end, you have like this pattern, right? Etched area will be etched, right? So what you see at the end, right? If you want to deposit using the negative photoresist, right? And then you should protect the deposit area like that. And then, but if you want to like etch out the masked area, then you should use negative photoresist, and then at the end you have etched the protected area, right? So that's the way kind of you can make either etched pattern or deposited pattern. Okay. Okay. Well, there are so this is kind of example then to make the MEMS for the photoresist patterns. First, the masking is necessary. So, well, it's a mask material. It could be right. So, well, so to mask to deposit the mask process, uh, you have either subtractive way or you have additive addition, and you have either subtraction or addition. Okay, so for example, um, for example, if you want to use photoresist as your masking material, and then PR is applied on top of the layer to be patterned, and then unwanted material is etched away, right? If you put after expose, and then you have to develop, and then you put this into the right, then into the etching, then exposed area will be unwanted material will be etched away, right? On the other hand, the desired material is deposited onto the patterned photoresist area, and unwanted material will be lifted up when resist is removed. So that's the so that's the way you can make a pattern. So SU8 is the most general negative photoresist. So this is the good material for making structure. So photoresist, this kind of photoresist is very unique because it works as like a photoresist first, and then after that, if you do a couple of curing process, this could be useful for any MEMS microstructure as well. So these are the kind of example here. People actually pattern the SU8 structure, and then they keep using it as like a certain structure. Okay, so that's the uniqueness of SU8. That's one of the general negative photoresist. Okay, and then so I just talked about this negative and positive photoresist briefly. Then this slide talk about a little bit more detail about the each process. Okay, so photoresist is kind of a resin. It has resin that's this resin is well, so photoresist, there are three components in the photoresist. So there is a resin, and then there is a photoactive compound inside, and then there is solvent. So these three materials was kind of mixed together to make a photoresist. Okay, so the resin basically provide the like provide good mechanical properties, right? So that's the contribution by the resin. Okay, like good, it should be stable, so it should be good adhesion, and then provide some robustness like mechanical properties, mechanical structure. Okay, and the other had solvent provide like some provide this is provide for to lower the viscosity of the resin and then the photoactive compound, right? During when you apply the photoresist on the wafer, actually you drop the photoresist and then you spin the wafer. So during the spinning, with high spinning, actually the solvent, the photoresist should be spread out from the center to the edge of the wafer. So if it's not viscosity is not low enough, right? The spread the spread of the photoresist is not uniform spread. So that caused the like a thickness non-uniformities over the center to the edge of the wafer. Probably the around the center is a higher thickness comparing the less thickness at the edge, right? So you need a certain low viscosity, right, and the photoresist. To do that, you should mix with solvent, right? That's the contribution of the solvent. After actually after developing, actually solvent will be removed by the heating, so you don't really worry about the solvent over the next process. Okay, okay, and then resin and solvent, and then the photoreactive compound should be mixed. So there is two kinds, right? As I explained, one is the positive photoresist, and the other one is the negative photoresist. Okay, so for the positive photoresist, there is also two type of the photoresist is available. One is polymer chain scission, and then the other one is functional group changes by the exposed, right? So exposed area was the like so by exposed of UV light, then this positive photoresist, the polymer chain was like disconnected, or functional group was changed. So in that way, to make the exposed photoresist easier to remove. Okay, that's the way the positive photoresist. The other hand, the negative photoresist, actually, there is two kinds. One is the cross-linking, and the other way is a hydrophobicity changes. So by the UV expose, the exposed area, actually their cross-linking was like enhanced. Okay, so they after having the UV light for the negative photoresist, they have become hard to remove because this cross-linking. That's the same as the hydrophobicity also changing. So those are two characteristics could be useful for the negative photoresist. Okay. So there is more detail about the positive photoresist. So there is a Novolac. There is called Novolac, and that's the polymer resin. And then this is kind of general material that used for the resin is Novolac, and then the photoactive compound is a diazo. We call this DQ, and then diazoquinone. That's the we call usually DQ. That's the photoactive compound for the positive photoresist. Okay, and then so we mix with these two like as a resin and then as a photoreactive polymer. Okay, and as a polymer as a cleanroom user, I have been using these two material during my process. But I'm not really good at it's a polymetric structure. But I try to my best to explain to you. So this resin actually in aqua solution and dissolved in aqua solution easily, and then solvent added, but most solvent is evaporate at people exposed. So this polymer resin is in aqueous solution, is easily dissolved in aqueous solution. Okay, while providing as a roll-up resin, and this DQ is the occupied about 20 and 50% of the photoresist, and then it is insoluble in base solution. And then by UV light, this is become to insoluble. If you, this is like it's a molecular structure, and then if light is coming in, then its structure is changed like this. Like this is UV light, and then and then during the hydration, and then there is two steps during the developing in hydration first, and then it was developed. Okay, so exposed area is kind of removed in this process. Well, advantage of DQN combination is it has good resolution with the near UV light, and then Novolac is chemically resistant, and then environmentally friendly as well. So that's the good things for DQN. For the negative photoresist, comparing to the positive photoresist, it is a relatively good adhesion to substrate. Okay, so if you need a really strong adhesion to the substrate, like you keep using this photoresist for subsequent etching process for a long time, then certainly negative photoresist has an advantage over the positive photoresist. Okay, also it has a relative resistance to chemicals and plasma etching. So if you apply this chemical or plasma etching process for a while, and then negative photoresist has advantages. And also it has good mechanical structure, mechanical properties. So that's why people keep using even this photoresist as a mechanical structure for MEMS. By the way, the disadvantage is like that. Okay, Well, there is a little volume changes during the developing. Okay, so um, so they recommend the minimum feature size about 2 micron. Okay, so because if you're making smaller and smaller, then because it's swelling, your kind of a pattern resolution is not good. Okay, and then developer usually organ solvent that is not a good good environment, right? It's an organic solvent. Okay. Also, it's difficult to remove. That means, if you are working as a like clean room user, before you really familiar with your process, actually if you wanna recycle your wafers over and over again, then the removing negative photoresist is problem. So relatively positive photoresist is much easier to remove. Just dip into the solvent and then just clean it, and that's it for the positive photoresist. But negative photoresist, you have a couple of more steps to remove because it's hard to remove. That's why it's good for the adhesion, right? So you have advantage and disadvantage at the same time. So SU8 and then Future X is two representative good negative photoresist. For the SU8, it is really thick. If you are using SU8, you can make like a thick and high aspect ratio structure and good mechanical properties. So if you want to make thick, high aspect ratio structure as a photoresist, SU8 is really good. So there is some number of the product, and then there are two kind of product is available. Then the Okay, and then for the Future X is a uh, relatively easily removable comparing the SU8, and then its vertical profile is good in control. So it's good for the lift up process, and then it is developed based on the water-based developer called LD6. For the SU8, you use the Gireland-based developer called PG MEA, right? This is like a product name. Or sometimes dry film photoresist are available, but we're gonna skip the discussion on this. Okay, well, so UV light is the light range, the way the wavelength is range from 350 to the 500 nanometer. So okay, so it's I mean you can basically it's not visible. Sometimes people start using the deep UV light. This is range of about 150 to 300 nanometer because deep UV light has a shorter wavelengths. So basically, you have a higher resolution is available because the resolution usually depends on the wavelength of the source. Uh, uh, just kind of a rule of thumb is you can reach the half of the wavelengths uh, because it's the optical diffraction limit, right? So basically, if you keep downing like uh, less wavelengths, then you have chance to have a higher resolution of your pattern. Okay, and then to generate UV light, and then for example arc lamp filled with mercury, you have like H line, and you have like I line that you can pick. You can filter it out at the other wavelengths, and then you can use this to pick of the in UV range to use like a source for the UV. Or xenon sometimes is used for the deep UV as well. Okay. So the UV is not good for your health, right? So usually when you during the exposure of UV light to the vapor, usually the users like a turn away from the source. So to just try to avoid any physical eye contact to the UV light. Otherwise, you have affected from the UV light. Okay. Well, this is the way to expose, like you have contact printing and you have a proximity printing and you have projection printing. So contact printing, you have like physical contact between your pattern on the mask to the PR, photoresist. And then proximity printing, you have a little separation between the two, but at the same time, you have full resolution to the light diffractions through because of this gap, right? And sometimes you have a projection printing, like you wanna squeeze your pattern into the like a smaller pattern on the wafer. So basically, uh, you kind of scale down your pattern through the optics, and then you scale down. So we call this is like a stepper. So if you wanna like for example, on 6-inch wafer, if you want a pattern certain size of the pattern repeatedly on the wafer, this projection printing is good. Having like the my pattern of the mask is kind of squeezed down into the small area of the wafer. So I mean, and during the procedure, normally you're going to use like contact printing or proximity printing, right? Okay, let me stop the talk because it's more than 25 minutes past. Okay, let's continue the talk later.